Okay, today class we're going to talk about ratios and unit rate. So the TEKs that we're going to talk about today are 7.4c, which is calculate unit rates from rates in mathematical and real-world problems. But the big one that we need to focus on today is determine the constant of proportionality. That's the new thing that we're dealing with in 7th grade, constant of proportionality. We'll learn what that is in just a few minutes in the lesson. But it comes with a nice little equation. K is equal to y divided by x, or dependent divided by independent. We'll talk about that a little bit later on in the year as well. Okay? So our lesson today is a PowerPoint, so let's see if we can launch that. We're going to focus on ratios and rates. So today in our lesson we're going to learn to find units, compare unit rates such as average speed and unit price. This will be about a 10-minute lesson, so just kind of be prepared for that. Okay? So first, let's kind of look at it at an example. Okay, in basketball practice, Kathleen made 17 baskets in 25 attempts. She compared the number of baskets she made to the total number of attempts she made by using the ratio of 17 over 25. A ratio is a comparison of two quantities by division, a very important definition. A comparison of two quantities by division. Now, the most common form of writing a ratio is a fraction, but there are two other ways of writing a ratio. We can write it as a fraction, and the reason why we do write it as a fraction is because we can determine if it needs to be simplified a lot easier. We can also write it with a TO and with a colon. But the one point I want to talk about with this one, this 17 over 25, is it a true fraction? In this particular case, yes, it is a true fraction. A true fraction is going to be part over total relationship. So in this problem, she made 17 baskets out of 25 total attempts. So this is a true fraction. But a ratio doesn't have to be a true fraction. It's just a comparison of two quantities, and it doesn't have to be part to total relationship. So let's see if we can actually do one of those real quick. In this particular problem, it says 20 students are asked to choose their favorite music category. 8 chose pop, 7 chose hip-hop, and 5 chose rock. We want to write a ratio in all three forms. On this particular one, we're looking for what is the ratio of rock to hip-hop, and that tells us how we need to write them. So we look up in the top and we find out how many students chose rock. It says 5 chose rock, so we would write it as 5 over. And now we look for hip-hop, and it says 7 chose hip-hop, so that's 5 over 7. Now that 5 over 7 looks like a fraction, but it's not a true fraction because it is a part-to-part relationship, 5 over 7. So when we write it out as 5 over 7, we can write it all three ways, 5 over 7, 5 TO 7, 5 colon 7. That is review from what you talked about in 5th and 6th grade. Very simple, very easy thing, writing a ratio. But what we want to focus on today is rate, unit rate, and that new thing we talked about there, constant of proportionality. And that's going to be the big one. So let's look at a couple more definitions. A rate is a ratio, so we know it is a comparison of two quantities. So it's a ratio that compares two quantities measured in different units. So this is the key to a rate. Every time you pass a gas station, you see a rate because we're talking about dollars per gallon. A unit rate is a rate whose denominator is 1. So unit means that we want to compare everything to 1. Okay, and the way we do that is to change a rate to a unit rate. You divide both the numerator and denominator by the denominator. So we take top and bottom and we divide by the bottom. And that's really all we have to do. Now here's that big term that we talked about, constant of proportionality. A unit rate is also called a constant of proportionality. Okay, so again, we'll talk about that more, but anytime in context of rates and unit rates and things of that nature, ratios, when we talk about a constant of proportionality, I'm really just asking you to find what is a unit rate. Okay, there'll be more to that a little bit later on in the semester. So let's see if we can do one or two questions real quick, and then we'll move on. Okay, a Ferris wheel revolves 35 times in 105 minutes. How many minutes does one revolution take? Well, what I want us to do in this particular one is I want us to find a unit rate. How much for one? Okay, so when we look at this, it says Ferris wheel revolves 35 times in 105 minutes. Our question tells us what our ratio needs to be, or what our rate needs to be. How many minutes to revolutions? So that tells us that the 105 needs to go on the top, and the 35 go on the bottom. Okay, so what we need to do with this then is we take the 105 and the 35, we write that rate down, and then what we do is we divide both top and bottom by the 35, and we end up with 3 minutes per revolution. Okay, so that's what the question asks. How many minutes does each revolution take? For each time for that Ferris wheel to go around in a circle, it's going to take 3 minutes. So a Ferris wheel revolves one time in 3 minutes. One more real quick. Sue walks 6 yards and passes 24 security lights. And this one, we're not talking about 6 yards as in each 3 feet. We're talking about like front yards. Passes 24 security lights set along the sidewalk. How many security lights does she pass in 1 yard? Well, again, we have to set up our proportion. If you look at the question, it asks how many security lights per yard. Okay, so that means we're going to do 24 over 6. We divide both top and bottom by 6, and we find out that there are 4 lights per yard, 4 security lights per yard. We just kind of run through this real fast so that we can get on with the next part of the lesson. So the next part says an average rate of speed is a ratio of distance traveled to time. The ratio is a rate because the units in the numerator and denominator are different. Anytime we're talking about a rate of speed, I want us thinking about a particular formula that we've used in both science and math, and that is D equals RT. Distance equals rate times time. Distance is always going to be determined by the rate of speed in which you're traveling times how long you've been traveling that speed. Okay, so if you are going at 60 miles an hour, that means that I should travel 60 miles in 1 hour's time. So if I change the time to 2 hours, 60 miles an hour over a 2-hour time period, I should have traveled 120 miles. 3 hours, 180, and so on and so forth. So anytime we're dealing with speed, I need you thinking about distance equals rate times time. So in a problem like this is Danielle is cycling 68 miles. It's a fundraising commitment. She wants to complete her ride in 4 hours. What should be her average speed in miles per hour? Okay, so in a problem like this, we need to set up a ratio. Okay, we need to set up, we want to go 68 miles in 4 hours time. So that's what we do. We write the rate, 68 miles divided by 4. Okay, now we need to figure out how far do we need to travel, or how fast do I need to travel per hour. Okay, so that's when we divide both sides by 4, and we find out that she needs to travel 17 miles an hour, or average a speed of 17 miles an hour. So at the end of 60 minutes, she should be 17 miles into her ride. At 2 hours, she should be at 34 miles in order for her to be on track to finish in her 4-hour time period. Rhett is a pilot and needs to fly 1,191 miles to the next city. He wants to complete his flight in 3 hours. What should be his average speed in miles per hour? In this one, we do the same exact problem. We look at our ratio here, and it says it in words, what it needs to look like, miles per hour. So that is miles divided by hours. So we write the rate is 1,191 miles in 3 hours. We divide both sides by 3. Or both top and bottom by 3, and we find out that he needs to travel 397 miles per hour in order to meet his goal. Okay. Unit price. This is the most important part of today's lesson. Unit price is the price of 1 unit of an item. The unit used depends on how the item is sold. The table shows some examples. Liquid items are normally sold in ounces, quarts, gallons, liters. Solid items, ounces, pounds, grams, kilograms. Any other item, sometimes it's going to be by the bottle or by the can, by the container, those kinds of things. So what if we had a problem like this? A 12-ounce sports drink costs 99 cents, and a 16-ounce sports drink costs $1.19. Which size is a better buy? Whenever we shop, we always want to get the best bang for our buck. We want to make sure that the money that we're spending is of value, and we get the best out of that. So here we have 2 quantities, a 12-ounce quantity and a 16-ounce quantity. And neither one can we really compare because they're different sizes. So what we have to do is figure out a way to compare these by looking at the same size thing. Well, one thing that we can do is, if I know 12 ounces is $1.99, if I found the unit rate, how much for 1 ounce, and if I did that also for the 16-ounce bottle, I could figure out how much it costs for 1 ounce. I could compare those because they're a single ounce. So what we're going to do is we're going to set up a ratio. 99 cents divided by 12 ounces and $1.19 divided by 16 ounces. That will be used to find our unit rate. And the way you do a unit rate is always price divided by quantity. And you find out that the 12-ounce bottle is about 8 cents per ounce, and the 16-ounce bottle, it's about 7 cents per ounce. So which is the better buy? We find out that the 16-ounce is the better buy in this case. And this is how gas stations get you. They know that we typically think that bigger is always better, or bigger is always cheaper, or more of them. If I get more of them here, it'll be cheaper per the ounce. Well, at a gas station, whenever you look at your soft drinks and things of that nature, they know that you think bigger is better. So sometimes they will make the bigger product a little bit more expensive per ounce, okay, than the smaller ones, because they know that you think that way, and they want to get as much money out of you as possible. So get one more, and then we'll finish this lesson up. A 1.5 gallon container of milk costs $4.02. A 3.5 gallon container of milk costs $8.75, which is the better buy. So this one we do the same thing. $4.02 divided by 1.5, $8.75 divided by 3.5, because what we want to find out is how much is it per gallon. So the 1.5 gallon, we find out it's $2.68 per gallon. In the 3.5 gallon, we find out it's about $2.50 per gallon. So that means that the 3.5 gallon is a better buy. However, for me and my family, we don't drink that much milk. I would still buy the 1.5 gallon one, because I would end up with 3.5 gallons throwing some of it away because it would ruin, because we just don't drink that much. So sometimes the better buy is not really the better buy for you. You got to think about that whenever you're shopping. Okay? So in this lesson, the big thing is price per gallon, unit price, and comparison shopping. Those are going to be some things that we're really going to focus on in this lesson. So let me get out of this PowerPoint and go back to our homework. So for our homework, we've got 10 questions here, 10 questions that we need to answer. Okay? So what I would like for you to do on a problem like this first one says a part-time job pays $237.50 for 25 hours work. I want to know how much money does the job pay per hour. So what I want you to do is set up the ratio. In this case, we're going to set up the rate of 237.50 divided by 25. And then I need you to change that to a unit rate. So at this point, we get out our calculator. We do our division, $237.50 divided by 25. We find out we get 9.5. So that means that we get 9.5, but we're dealing with money, so we need to put a dollar sign and we need to put a zero, because we need to remember money is to the hundredths place. And then we also need to tell me this is $9.50 per hour. Each answer should have 2 labels on it. For the first 5, you do them exactly like the first one. 6, 7, and 8, again, exactly like that first particular question. On 9 and 10, you'll notice that on 9 we've got a 12-ounce jar, a 16-ounce jar, and a 24-ounce jar. So we're going to need to figure out which one is the better buy. So you'll do 3 problems, 865 divided by 12, 1099 divided by 16, 1699 divided by 24, and you circle whichever one is the better buy. Number 10 is the same way.